Hello everyone. In the last video, we saw about what is perceptron, why perceptron is a step function, what is linear separability, what is the XOR problem, and we also created a simple code where we trained our neural network or trained them to give the output of an AND gate. Today, we will see what all things are needed when we move from the perceptron to the neural networks. Now, I'll just give you a simple example. Let's say you're working with images and you are having an image which is full of cats and dogs. You want to train your model in such a way that you just want to get an output in the form of cats and non-cats. There is nothing called as dogs for now. But if you do this in the terms of a perceptron, which is a step function which cannot learn gradually, in that case, let's say you are bringing a cat where you want the output as this is a 90% cat and a 10% dog, but you will not get such output. Abruptly, the output is going to change. This is where we say that the perceptron is having the disadvantage. It cannot gradually learn. It will give the output only in terms of zeros and ones. There cannot be anything in between. So my output can be 0% or 100%. You cannot get an output as, okay, there is a 70% chance of this image to be a dog and not a dog. 70-30. 50-50, so these probabilities will not come into picture. Now, if I give you the diagram of a simple step function, it is in this way. Either it can be yes or it can be no. Even a step function is as like 1 and minus 1. Even if it would have been 1 and 0, it would still be called as a step function. But to train a model, to make your model learn, we need something different, something smoother. We need a function that progressively changes from 0 to 1 with no discontinuity. If you remember your elementary maths, discontinuity, we mean that our function should be differentiable at each and every point. Mathematically, this means that we need a continuous function that allows us to compute the derivative. Now let's learn actually how a neuron or a neural network, one in the bio and other is the engineering, how it works. If I talk about a biological body, we can see that there are the dendrites which are carrying the impulses towards the cell body, and then there is the axon terminals. Impulses are carried away from the cell body. Now if I give you a simple example, I am touching you on your right hand. Your right hand has a sensation. This is because there must be something which is actually triggering that point and your left hand is not responding. Because I've touched you on the right hand. Therefore, this means that there should be a threshold value above which there is a trigger. This is where the concept of activation function comes into picture. In artificial neural networks, the activation function of a node defines the output of a node given an input or a set of inputs. A standard integrated circuit can be seen as a digital network of activation functions that can be on or off depending on the input. Now if I talk about a simple neural network or the perceptron that we studied in the last class or the last video, we can say my input is coming in the form of x0, w0, w1, x1, w2, x2, so on till wn xn. Therefore, my total input which is going to the neuron is my sigma or the summation of wi xi plus b. This particular output will get now multiplied by an activation function which will actually decide that whether your next neuron or the next layer of network will get triggered or not. So here comes the need of the activation function. Now let's try to understand what are the different type of activation functions, where we can use them, and what are the advantage and disadvantage of those type of functions. Firstly, let's learn about the non-linear activation function. The first one which we would be interested is the sigmoid function or the logistic function. If I talk about the equation of a sigmoid function, it is nothing but 1 divided by 1 plus e to the power minus input. You can see the graph where we are saying that my input, maximum output that I get with the positive input is 1 and the minimum is 0. So the sigmoid is varying from 0 to 1. But you can also see that there is a gradual increase from 0 to 1 and there is no sudden increase that was there with the step function. The main advantage of this sigmoid function is that there is a smooth gradient which prevents the jumps in the output values. Output values bound between 0 to 1, normalizing the output of each neuron. There can be clear prediction. For example, in this particular graph, for x above 2 or below minus 2, it tends to bring the y value, that is the predicted value, to the edge of the curve, very close to 1 or 0 depending upon what is your input. Either it is greater than 2 or it is less than minus 2. This enables clear predictions. But disadvantage is that this suffers from the vanishing gradient problem. This means that for very high values of x or very low values of x, there is almost no change in the prediction, causing the vanishing gradient problem. This can result in the network refusing to learn further or being too slow to reach an accurate prediction. The outputs are also not zero-centered, and this type of activation functions are computationally expensive. Now let's try to understand what is a tanh function and how it is different from my sigmoid function. This tanh function, as you can see from the diagram, the output lies between minus 1 to 1. The main difference between the tanh and the sigmoid function is that this is from 0 to 1, but this is from minus 1 to 1. So the main advantage is it is zero-centered, making it easier to model inputs that have strongly negative, neutral, and strongly positive values. Otherwise, it is quite similar to the sigmoid function. Now, let's move to the next activation functions. The most important and the most widely used activation function nowadays is the ReLU function. By ReLU, I mean that rectified linear unit. If you see the graph, it's like your output is equal to your input for any value where your input is positive, but it is squashed to 0 for any negative input. It is computationally very efficient. It allows the network to converge very quickly. It is non-linear. Although it looks like a linear function, ReLU has a derivative functions and allows the back propagation. But still, the main disadvantage of this ReLU function is the dying ReLU problem. This means that when the input approaches to 0 or negative, the gradient of the functions becomes 0. The network cannot perform back propagation and hence it cannot learn. The next important function or the activation function after ReLU is the leaky ReLU. The graph is quite similar, but the main difference is that even after 0, it tends to go below and it is not exactly equal to 0 for any input which is negative. This prevents the dying ReLU problem. This variation of the ReLU has a small positive slope in the negative area, so it does enable the back propagation even for the negative inputs. Apart from this particular advantage, it is quite similar to the ReLU. Results are not consistent. Leaky ReLU doesn't provide the consistent prediction for the negative input values. So now we have learnt about four important functions, that is the sigmoid or the logistic, then is the tanh function, then is the widely used ReLU function, and there was certain disadvantage of the ReLU due to which leaky ReLU came into picture. So this is mostly about the different activation functions. But there are certain terminologies which we should know before we actually make up the first neural network code. Now, there are certain parameters for compiling of the model, and while we learn this compilation, we will come across some important terms. The choices that is to be made during a compilation is that firstly, we need to select an optimizer, that is a specific algorithm used to update the weights. Now there are various optimizers like that of the Adam optimizer and many other things. What type of optimizers and how the optimizers work, we will learn in the following lectures or the following videos. Second important thing that we need to choose is the objective function. By objective function, I mean the loss function, which is nothing but actually the difference between the predictive part and the actual part. So, we need to select an objective function that is used by the optimizer to navigate the space of weight. Frequently, objective functions are always called the loss function, and the process of optimization is defined as a process of loss minimization. Then we need to evaluate the trained model. Now, let's go through some of the terms. Before that, let's see what are the few objective functions that can be used. If you remember a simple regression statement, we used to use the MSE, which is nothing but the difference between the actual output and the predicted output. We are squaring it, hence even if there is a small difference, it can be easily seen as a huge difference. So this makes easy for us to have the value correct. So we should have this MSE as minimum as possible to have a good accuracy. Then comes a binary cross entropy. You must remember in the last lecture when we were creating a simple gate from scratch, we used this particular function as our objective function. So this is actually a loss function or an objective function which is used when we try to classify only two types of output, that is yes and no or 0 or 1. Similarly, when we are having multi-categories, we can use the categorical cross entropy, which is nothing but the minus sigma of Tij log of Pij. So these are some of the few objective functions. Now let's understand two important terms which is called as the epoch and the batch. This concept is very important because while we do the code, we should know what is an epoch and what is a batch so that we can have some sensible values within it. Let's assume you are having a data set which is having 100 rows or 100 records. You choose a batch size of 5 and 500 epochs. Now, what does this mean? This means that the data set is going to be equally divided into 20 batches as you have chosen the batch size of 5. This 20 number is coming from 100 divided by 5. So now when your data set is divided into 20 batches, that means each and every batch will be containing 5 samples. The model weights would be updated after each batch of 5 samples. This also means that one epoch would involve 20 batches or 20 updates to the model. With 500 epochs, the model will be exposed to or passed through the whole dataset 500 times. That is a total of 20 into 500, that is 10,000 batches during the entire training process. I think by now you are quite clear what is the difference between an epoch and a batch. So, by definition, epoch, it's a number of times the model is exposed to the training set. At each iteration, the optimizer tries to adjust the weight so that the objective function is minimized. Batch size, this is the number of training instances observed before the optimizer performs a weight update. So now we know what are the different activation functions. Few objective functions also we are aware of, and now we know the concept of epoch and a batch. Let's jump off to the code to make the most simple neural network. The first part of the code is just importing some of the values or some of the packages. So first I'm just importing NumPy, then I'm importing the MNIST datasets from the Keras. I will be trying to use the sequential model. There are two types of modeling in Keras. We will be explaining this in the next set of videos. As a layers, I'm trying to import two things. One is the dense and the other is the activation layers. As an optimizer, I'll be using the SGD optimizer, which is known as the stochastic gradient descent. But how it works and what is the actual algo, I'll tell you further. I'll be importing the keras.util, and this is the normal random.seed, which is used for the reproducibility. Now we have to define what is an epoch. We have to define what is the batch size. We have to define how many classes are there. And by classes, I mean that what is the number of output. Now if this is an image, so we have imported the MNIST dataset. I think everyone is aware in this particular dataset, we are trying to check the numbers. So there are total 10 sets of numbers. So that is why my classes, that is the number of outputs, equal to the number of digits, which is 10 sets of digits. The optimizer that we are using is the SGD optimizer. Hidden is 128 and the validation split is 0.2. That is how my train and test set is divided. Now, first we are dividing into train and test set. Now the most important part which I want to highlight in this code part is that we are dividing or normalizing my X train and X set. Then each pixel are normalized in the range of 0 to 1, which means that the intensity of each pixel is divided by 255, the maximum intensity value. The output is 10 classes, one for each digits. Then we are using the model, that is the sequential model, and model.add, and what we are adding the dense layers, and then we are reshaping it. The activation function which we are using is the softmax function, and then we are checking the model summary. The final layer is a single neuron with an activation function of softmax, which is nothing but the generalized version of the sigmoid function. The softmax squashes the k-dimensional vector of an arbitrary real values into a k-dimensional vector of real values in the range of 0 to 1. In our case, it aggregates 10 answers provided by the previous layer of 10 neurons. So now I have imported my dataset. I have divided into test and train. I have normalized it. I have defined my model to be a sequential model. Then I have added my networks, that is my hidden layers. NB classes, I have already defined it before. Then I am using the activation function as a softmax function, and then I will be trying to see the summary of my model. At the end, I am just fitting my model and also setting the parameters of my epochs and the batch size. I think this we are pretty clear with the concept of these. Then to score the model or to evaluate the model, we will try and print the test score, that is 0 and 1. So that first 0 means the test score and score 1 means the test accuracy. So this is the base code of a simple neural net with the Keras. I'll upload the code on the GitHub because in the video maybe you will not be able to copy paste, and also I'm having some comments, so 100% of the code may not be visible. So it is easy for you to see the code from the GitHub. And now I think it's a very good time for you all that you now know how you can design a simple neural network even on the image data, because MNIST is the image data and you are trying to detect whether the image digits that you have written is 1, 2 or what type of digit it is. So I think congratulations, everyone knows how to create a simple neural network now. Let's understand more concepts, more terms in the next videos, and then we will be stitching and marrying the data with each other so as to understand the full flow of the neural network. Thank you. Please let me know for any doubts in the comment section. I'll be happy to help you. Thank you, everyone.